and what's under this is fine, but this itself is the devil. It is already extremely difficult just to define the square root of this guy right over here. Now imagine how difficult it is to define anything like this, let alone something like that. So that is exactly why we do not choose this, we choose that, because this guy is a lot more convenient to define, because this operator applied twice, this operator applied twice, this operator applied twice. Simple as that. So how does this commute? How do we know that? Well, here's what happens when we write it out with, say, Lx. This becomes Lx squared plus Ly squared plus Lz squared. And since angular momentum, like all of the operators we've looked at so far, is a linear operator, we can rewrite this as Lx squared commuted with Lx, Ly squared commuted with Lx, Lz squared commuted with Lx. And of course, this is just Lx cubed minus Lx cubed. An operator commutes with itself, which makes that 0. And these other two are a little bit more interesting. What happens with them? Well, consider that this is equal to Ly squared Lx minus Lx Ly squared, and that over there is equal to Lz squared Lx minus Lx Lz squared. Is there possibly anything you can do to simplify these into the commutators that we actually know? Well, indeed there is. What is this commutator right here? Well, remember, it's Lz Lx minus Lx Lz. Now, compare and contrast that with this guy over here. Lz squared Lx minus Lx Lz squared. What happens if we just multiply this by Lz? Is this Lz Lz Lx? So that gives us Lz squared Lx minus Lz Lx Lz. Yikes, what the heck is this? And where's the other term? So it means we're missing something. And that specific something is just Lz Lx Lz. Because once we add that in, we get plus Lz Lx Lz minus Lx Lz squared. Exactly the terms we were. And we get Lz Lx